So good morning students. So I welcome you in the lecture series of electronics and device and circuit. Let me choose the pen first and then we will start with our lecture. So electronic device and circuit. So till that what we have seen, we are seeing the DC biasing of BJT. This is very important topic. Okay, very important technique. There are 5 techniques are there. If you are 5 technique, if you are well known to this, well you are familiar to this technique, then the entire DC subject is very easy for you. Very easy for you. But the thing is that you must know the 5 techniques of DC biasing of BJT. If you know the thing, then you will find the AC biasing. Okay, so the basic thing is that you must know the DC biasing of any transistor, and then you can solve any problem based on this one. Okay, so if you are not subscribed my channel, please go to the subscription. If you are subscribed, then you are getting the latest update of each and every video which I uploaded on my YouTube channel. So from this you can browse to the playlist and you can watch the entire series of EDC, then micro engineering and discrete time signal processing subject. So we have seen the biasing technique, so this is covered. If you are still having doubt, so you can browse to the playlist and you can watch the entire videos related to the EDC. So these are the 5 techniques are there, that is fixed bias, emitter stabilized bias. So we have what we have did, we have solved theoretically derivation of this one, and in this today's lecture we will solve problem based on this. So problem based on this we have solved. Then upcoming lecture we have started with the collector emitter loop. Then we will solve the voltage divider bias and voltage divider bias with feedback, collector feedback it is called as. So these 5 techniques are there. These are very important. You have to watch the videos if you are not watch the videos for fixed bias and emitter bias theory, as well as I have solved one problem based on the fixed bias technique over there. Okay, so this is the fixed bias. Okay, fixed bias, and this is emitter feedback. So what we have done, we have solved this configuration by IB is equal to what? VCC minus VB RB plus 1 plus beta RE over there. So this circuit is more stable than the previous one, because what will happen, this is to end the denominator. Now the IB value, if this RE value is increasing, okay, increasing, so this IB value is decreasing over there. IB value is decreasing. So this value is totally independent. Okay, these two values, because of in the previous case what will happen, this IB is totally dependent on my VCC and my RB over there. Okay, only single transistor, only single resistor. But now what will happen, if the value is changed by some days, we know that as days are passing, this value will be changing, because its resistance is plus minus 10% over there. Okay, or 5%, plus minus 5% its tolerance is there. So there are chances to its value will be changed after certain time. So to make the circuit very stable, we have to make the circuit which will not depend on the single quantity, that is not on RB, it should be also equal on RE also. So if this will change, by maintaining this value of RE, the circuit will be more and more stable over there. So IB is equal to what? VCC minus VB divided by RB plus 1 plus beta RE over there. Okay, so so what is there in this case? We have applied a KVL and we have obtained the value of VCC. VC is equal to VCC minus IC in bracket RC plus RE over there. So we will solve problem based on this first. So from this network, so now by seeing the diagram, what you have to do, you must able to identify the circuit, which kind of circuit is there. Don't mug up the formulas. Just what you have to do, we have to apply KVL across this one. Okay. So from this, what you have to do, we have to find out the value of IB, IC, VC, then VC, VE, VB and VC. These 5 values we have to calculate. Find out 3 and 3, 6 and 7 values you have to calculate. In the exam, at least you will find a 4 value you have to calculate for how much? 10 marks. So this is a big deal. 10 marks you have to calculate. So how to start with? We have to apply KVL as input side. So first of all, cut out this capacitor, cut out this capacitor, cut out this capacitor. Wherever there is capacitor, cut out. This portion will be vanished, this portion will be vanished, this portion will be vanished, this capacitor will be vanished, because it is open circuited. So remain circuit is like this one. So if I am applying KVL across this one, so input side will be like this one. I will draw over here. Just a minute, I will rub this portion first and I will draw for you. So this circuit is like this one. Okay, so this is my RB. So if resistor is there, so it causes current cross to flow, that is nothing but my RB, IB, and from this VCC. Here RE, if resistor is there, it causes current cross to flow, that is nothing but my which current? IE. RE is there, IE is there. IE, not IB, okay. And here you will find our drop, that is nothing but my VBE. Okay, VBE drop is there. So if I am applying KVL across this one, so what will happen in this case? If I am applying KVL, I will get this thing. Okay. So if I am applying KVL, I will get this thing, but I will put the value of IE is equal to 1 plus beta IB. So I will get the IB is equal to VCC minus VBE divided by RP plus 1 plus beta RE. So this is the formula. So put the value of VCC. VCC is how much? VCC 20 volt. 20 volt port. VB is equal to always 0.7. Keep in mind. Then RB, how much? Value of RB is how much? 430 kilo ohm. 430 kilo ohm value of RB. Beta is given to you, that is nothing 50, and RE is nothing but how much? 1 kilo ohm. If I am calculating this value, so 20 minus 0.7 is how much? 19.3, and 480 kilo ohm. So near about 40.1 micro ampere is the current flowing through RB. That is nothing but my IB over there. And IC is equal to beta times of IB. So multiply this value by 50. So you will get the 2.01 milliampere. That is nothing but my IC. IC is how much? 2.01 milliampere over there. Okay. So we have to calculate the value of VC from this one because it is asked. So we have calculated these two values. Just I will rub this portion. Okay, this value we have calculated. This value we have calculated. So VC. So for VC we have to apply output at KVL at output side. So the output side will be like this one. How to draw the output side? This is my output side from separation. Don't modify anything in this diagram. Like this one. So this is nothing but my VCC, this is RC, this is RE, okay, and drop across this is nothing but my VC and E. Apply KVL across this one, so what we will get? I will get the VC E is equal to VCC minus IC RE plus RE. So VCC is how much? 20 volt minus RC we have calculated, IC that is nothing but the 2.01 milliampere. Then RC is 2K and RE is 1 kilo ohm. So if this is nothing but the 21K, 21K multiplied with 2.01 milliampere. So 20 volt minus 6.03. If you are using calculator, you will find this answer. You will find the answer. So that is nothing but the VC is equal to how much? 10.97 volt. VC is equal to 10.97 volt over there. So if you are getting the value, then remaining things are easy, very easy. So that is nothing but the VC is equal to VCC minus ICRC. So how we are getting this one? So this is nothing but the VC E is equal to what we are getting? VC E is equal to VCC in VC minus VE over there. Okay. So if I are calculating for what? VC is equal to what? VC minus ICRE, and if I am putting the value of VC is like this one, so we are getting VC is equal to VCC minus ICRC. So VCC is equal to 20 volt minus IC is how much? 2.01 that we have calculated over here. Then RC is how much? 2 kilo ohm. If I am putting the value in the calculator, I will get 20 minus 4.02 volt. So 20 minus 4.02 volt is how much? 15.98 volt. 15.98 volt you are getting. The answer is correct answer for my VC. Okay. Then what about V? V is how much? How we have calculated by same thing. VCE is equal to VC minus VE. So from this V is equal to what? If I am shifting to this side, so that will what will happen with this? This will become plus, and this is nothing but VC minus VCE. VCE. So this will shift to this side. So VC is equal to what? V is equal to VC minus VE. So VC is how much? 15.98, and VCE is how much? We have calculated 13.97. If I am subtracting, I will get V is equal to 2.01 volt. 2.01 volt over here. Or V is equal to how much? Calculate IE, and IE is nothing but what? IC. If I am multiplying this thing, I will again get 2.01 volt. You can either use this technique or use this technique. Then VB is equal to what? VB plus VE. So how we are calculating? VBE is equal to VB minus VE. So from this I will calculate the value of V. V is nothing but the VB plus VE. VB plus VE I will get. So VB is how much? 0.7 volt, and VE is how much? 2.01 volt. So from this I will get the value as 2.71 volt. 2.71 volt we are getting. So VCB is how much? VB minus VC. So VB we have calculated, that is nothing but the 2.71 volt, and VC is how much? 15.98 volt. 15.98 volt. So that is nothing but the 13.27 volt. That is nothing but 13.27 volt is the correct answer for this. So in this way we have calculated all values. So remember, watch the video carefully and try to solve the problem by changing these values. So thank you very much for attending this lecture. In the next lecture we will start with the very important technique and very much favorite technique, that is nothing but the voltage divider biasing. That is a 99% chances are there the problem you will find on this technique only, collector bias technique, voltage divider bias technique. Okay, very stable technique is there. So I think we will stop over there and we will start the voltage divider biasing in the next lecture. If you are still down, please watch the video once again and you will get the answers. Okay, so thank you very much.